Hi, welcome to Applications of Fluids Part 2. In this problem, I'll use some more fluid dynamics to show you how to use the equations and how to analyze systems. So this one's called the leaky bucket example because what we have here, as you can imagine, is we have a bucket and it's leaking water. So it's just letting the water kind of fall out. In this case, it's just falling out straight down as seen in this video right here. So we're given lots of measurements, how high this is, how tall the water is. We have the density, we have how much it's filled by, we have the radius hole, etc. like that. So let's calculate some values. So one thing is to figure out the speed at which the water flows out of the hole, the volume rate, how much water was collected, and then how long it took for the object to fall that distance. All right, so let's go ahead and do that. So they don't give you the actual area of this because always we can use the area equation. So we're going to use Bernoulli's principle to calculate part 1, which is what is the speed of the water at which is coming out of here. So just like in the other problem, we have like an A and a B. So with no real reason for naming this, I'll call this A and B. So when I use Bernoulli's equation, so let's go ahead and just write it out really quickly. I have to know some features. I need to know what pressure is involved. I have to know how fast the water is at each of those locations. And I need to designate a height at those locations like that. So let's analyze part A right here. So part A, clearly there's motion because the question's asking for it. Now at part A, this hole is exposed to the air, so that's atmospheric pressure. So we can write the first part, PA, as the atmospheric pressure, plus 1/2 the density of water times the velocity at A. So we can always choose our heights, and I always like to choose the lowest part as 0, and then let this part B be the highest point, H, right here, HB. Because by doing that, I don't have to do anything, I can simplify my problem. So I'm going to call the lowest point right in here my 0 mark. So with that said, this whole term, because I call this H0, is actually 0. So I'm going to put a placeholder here because HA, I'm going to call my 0 height right there. So then at part B, this is also exposed to the atmosphere. Because there's nothing else, I mean, besides the air itself, there's nothing else around here. So this is atmospheric pressure. This is going to be plus the speed of the water here. So interestingly enough, the velocity of the water at the top is 0 because it's not flowing. Now, yes, it's moving down, but it's not flowing from from here to here or going horizontally in any way. So at the very top, in the perspective of all the water to itself, it's not moving. So this is going to be 0. So this whole term, I forgot the V, sorry. This whole term goes to 0 there. So that's kind of nice. So then I'm left with the rho G H B, like that. So since these two terms are in the same spot, if I do -1 from the other, we'll find that this actually goes away. And then this reduces down to almost like, looks a lot like kinetic energy and potential, right? So, by the way, just coming back to this just to make sure I was clear, these are the same values, so they're just going to cancel each other out. The rows cancel each other out. And if I bring the 2 up, I get VA squared is 2GHB. And as you might imagine, VA is 2GHB, square rooted. So the first part, although it starts off with the complicated Bernoulli's equation, reduces down to something very simple. So the velocity at A is going to be the square root of 2 times 9.81 times the height. So let's go ahead and do that. Actually, I'm going to do it on the calculator again. 2 times 9.81 times 0.7, just like that. And then we have to take the square root of that. So let's go ahead and do that. I get 3.7 meters per second for the first part right there. So that's my velocity at part A. So let me just clear this off, move this down, and talk about the next question. So the next question says, what's the flow rate at which the water flows out of the hole? So flow rate, there's a couple ways we can use flow rate, or two equations. The first one is the area times the velocity. That will give us the flow rate. Or the other option is how much volume to divide by time. This is also flow rate. So looking at the two options we have at the moment, I hope you notice that we do have the area because we have the radius at the bottom. And conveniently, point A is solved for the velocity. So we can find the flow rate. So the area of the pipe is going to be pi r squared times the velocity, 3.7 meters per second, like this. So let's go ahead and solve this out. 0.001 times 0.001 times 3.14 times 3.7, like that. And what I get from the flow rate is a very small number, 0.1234116. 1234116. And this is in meters cubed over seconds, like that. So you could write this as 1.16 times 10 to the negative fourth meters cubed over seconds. So we can do it like that there. And that's the flow rate for that part. Part C says calculate the volume of water collected in the tray, so how much water we collect in 2 minutes. So notice that this is in seconds, so I need to convert my 2 minutes to seconds, so that's going to be 120 seconds. And notice that we can calculate the volume of the water if we know the time and the flow rate, which we happen to know. So 1.16 times 10 to the negative fourth meters cubed over seconds equals to the volume, which we'll calculate, divided by 120. So when I calculate that out, so I'm going to multiply this by 120, I get 0.139 to the negative third meters cubed. So that helped us calculate how much volume went into that bucket at that point. Oops, sorry. And then the time it takes to fall that distance from the bucket. This is a disguise of a kinematics problem. So we have a droplet of water, and it says that it falls 0.5 from the hole. So the time it takes to do that, so the delta x is going to be the 0.25 meters, like that. We're looking for time. The acceleration is that of the acceleration due to gravity. And then the initial velocity, since we're given that in the problem, will be the, so calculate the time it takes for a given droplet to fall 0.5 from the hole. So when we're doing this, we're going to consider the initial velocity to be 3.7 meters per second, which was what we saw for 4.8. So this becomes an ugly problem because technically we don't know the final velocity. We can't assume it's zero because it goes of course the problem's worded as 0.25 meters, so it's not necessarily at the ground, and it's going to be traveling a lot faster than, of course, where it started with 3.7. So the most direct way to solve this is to use this equation, but it's not the best way because you end up with a quadratic. But it does work if you use this. The way you plug it in is the 0.2. So notice I made it negative because it's falling. This is negative because it's falling. T is what we're solving for, plus 1/2, negative 9.81, T squared. So that's one way to solve it. When you do, you get 0.062 seconds. Or as always, the other option is, instead of doing it as the most direct way as one step, I mean, this becomes a lot of work anyways, to do 2 steps. So you could do the following. So you could use delta x as 1/2 vi plus vf t, where you solve for vf. And then what you can use, so do this as step 1, and then step 2, use this equation, now that you have vf, to solve for t. Oh, I'm sorry, you can't use that because you have 2 unknowns. My fault. You could do the following. Vf final squared equals vi squared plus 2a delta x. Sorry, my fault. You do have all of these. You have the acceleration, you have the change to solve for vf. And then we go ahead and use this one. So I like the second method just because I don't like dealing with the quadratic. So let's go ahead and solve this out. So I get 3.7 meters per second squared plus 2, negative 9.81, negative 0.25 meters. So let's go ahead and do that. Sorry, let's get this out of the way. So 2 times 9.81 times 0.25. So that gives us 4.9, so I'll remember that number. 3.7 times 3.7 squared plus 4.9 I forgot that number. So 13.69. So let's write these down. Here we go. Now that becomes positive because it's squared. So then this one is 2 times 0.25 times 9.81. Yeah, 4.905. So this is also positive, because the signs cancel there, so it becomes positive. So let's go ahead and add that up. So plus the 13.69, and then I'm going to square root that. So the velocity we got was 4.31. 4.31 or 4. Yes, 3.1. I messed that up, so let's just change that. So 4.31, like that. Oh, I'm running out of time. So V final equals V initial plus AT. So the final is negative 4.31. The initial is negative 3.7 because it's going down. 9.81 T. I could beat the clock. So what we have here is we're going to do 4.31 minus 3.7 divided by 9.81. there's that number 0.0